This conference will now be recorded.
Hello, everybody. Jordan Girth from the National Weather Service Office of Observations here for the Satellite Book Club Seminar Series. This is session number 14. Thanks for joining us. I hope you are staying well. Got another great presentation today from Dave Pogorzala, who is a remote sensing scientist with the GOES-R Product Readiness and Operations team. And he'll be talking today about caterpillar track, shark fins, and the Cookie Monster, a guide to the GOES-R ABI image artifacts. And I think I'm going to go raid my cupboard and get a cookie during this presentation. Just a reminder that this session is being recorded. After the presentation, there'll be a little bit of opportunity for Q&A, but if you have a question as the presentation is going on, feel free to type it into your chat window there and we'll make sure to get to it. We have Dr. Chad Gravel, Techniques Development Meteorologist at Southern Region Headquarters here to facilitate that discussion. Also just want to call attention to Chad for his, to give him some congratulations on his award from the AMS. He won the Francis Reichen Schelber Award for his work on GOES-R. And I wish that last name was easier to say, but the award is well deserved. Congratulations, Chad.
I appreciate that.
We are looking for future presenters and discussion facilitators for this. So if you have an idea, something that would be useful to your colleagues out there in the field, feel free to let us know. I'd like to also thank our training team, Brian Mata. If you have any questions or needs for training, please feel free to get in touch with him. Finally, thank yous are extended to our Tower Rest team, David Blutis and Lee Byerly, who have helped coordinate these calls, Office of the Chief Learning Officer, and the GOES-R and JPSS program. So without further ado, I'd like to introduce Dave, who joined GOES-R in 2011 as a member of the Calibration Working Group, supporting the analysis of the pre-launch ABI testing and modeling of the on-orbit performance. More recently, he's been the GOES-R Val Tool Manager and the ABI Image Quality Engineer, who troubleshoots the anomalies and prototype updates to optimize the image quality. So with that, Dave, welcome to the Satellite Book Club. Look forward to your presentation today.
Thank you. Just to verify, everyone sees the slides just fine?
We got you.
Excellent. Okay. So I've got sort of a lot to go through, so I want to dive right in. But before I get to any of the artifacts, I want to quickly walk through how it is we get the imagery we get from ABI, both with the instrument and the ground system. So photons that we're interested in make their way out to ABI, and within ABI, the focal planes consist of tall, skinny arrays of detectors, and each channel is separated physically from each other. And you see just my little example here, for the visible near infrared channels 1 through 6, you have 3 columns. For the infrared, there's 6. But for each row, only one detector element is selected at a time. This gives us redundancy for swapping out, which we'll see later on. The scan mirrors scan these focal plane arrays across the Earth and in a series of swaths. This is how we acquire our imagery. For a full disk, that gives us 22 swaths. A CONUS is 6, and mesos are 2 swaths. That data then is downlinked to our ground stations where we get to phase 2, the algorithms. The packetized and compressed data comes down. First thing we do is decompress that to reconstruct the swaths that ABI acquired. That gets calibrated to units of physical radiance. These get navigated, essentially geolocated under the Earth. Then resampled into the 0.5 kilometer, 1 kilometer, or 2 kilometer grids for the L1B products. Those then get scaled to reflectance or brightness temperature, and then sectorized and sent out, as well as onto the level 2 algorithms as well. So that's just a quick crash course. Some of these elements of the image chain from photons to products will come into play for some of these. So let's start with the infamous Cookie Monster, and hopefully everyone's having their lunch so they can get a cookie for dessert. Cookie Monster is the circular or semicircular missing regions of Earth, as you see here, as we go through nighttime with channel 7 example. This region moves across. This is very simply, we don't want ABI to look too close to the sun. There's onboard mechanisms that track the location of the sun and will automatically truncate each swath as needed, or omit swaths entirely if needed, to avoid looking too close to the sun. There is one thing to note: if because those different channels are separate from each other on the focal plane, that means the amount of truncation does vary by channel. So that's just something to be aware of if you want to do a multi-channel color composite by overlaying bands. And for mitigation, there is none. We very much want ABI to do this, and it does it great. But related to this, formal term is bright object avoidance. Related to this is stray light. This you can see it's pretty much constrained to channels 1 through 6 in the visible near infrared, and that shows up as a vertical bright streak, often coming out of the Cookie Monster bite. Sometimes you'll see it as a horizontal streak coming out as well, along with the vertical. Basically, this is due to unwanted photons scattering themselves in ABI's optical path, and they're not being cut off properly. So it is what it is. There's really no mitigation for it, but it goes by quickly, and it happens really only to the visible channels at night, and we're not really paying attention to those too much this time of day anyways. Next up, stripes. And I use that term carefully, stripes, because you'll see why next. Looks kind of like this, high contrast stripes that are isolated across the scene. This is a result of a bad detector, and you'll see this regardless of what the scene content is behind it. Bad detectors come in different flavors. It could be really noisy, it can saturate, or within the ground algorithms, some of the calibration parameters can go stale. And so regardless of how that happens, they tend to look kind of like this. To mitigate it and the duration of it, it sort of depends on exactly why it's happening. If it's a stale parameter and a product operator has the capability to catch that and issue a couple commands to flush that relatively quickly, and that usually clears it up if that's all it was. If it's noisy or saturated, I mentioned we have those redundant detectors for each row. We can issue a command up to the satellite to have ABI select one of the neighboring detectors, and that usually does it. That's a process that takes, 2 to 3 business days once you get the approvals and bundle the commands. There's a feature called the dead row list in the algorithms that would basically exclude the bad detector from the products. We're still working on getting that to work the way we want to and get it operationalized properly. So hopefully we can roll that out as a Band-Aid, so to speak, to mask this in a quicker turnaround. So those were stripes. Let's talk about striping. And yes, at least within my close circle, those are different things. Here you see, instead of an isolated high contrast stripe, we're looking at persistent low contrast and widespread striping. Typically, you only see this over uniform scenes like a hurricane cloud deck or dark oceans. And this is because for those detector arrays I mentioned earlier, those are anywhere from 300 to 1,400 detectors tall. And it's very subtle variations from one to another in how they respond to a uniform scene give rise to this striping. Calibration algorithms do largely correct for that, but early on we had some residual errors that nominally you don't see that except for certain scene content. You'll see this example is a few years old. That's because we have taken some actions to sort of compensate for this and correct it. There was some lookup table updates, LUTs, that were updated a couple of years ago. Also, we did a slight modification to an algorithm that's used when we do a solar calibration on orbit. And both of those have largely corrected this quite a bit. And if you look at hurricane loops from recent weeks, you'll see that we look really sharp and the striping is greatly reduced. One other option is something called a relative gains that one of the science teams developed. It's in work, largely it's ready to go, but it's sort of in our back pocket should we need it in the future. That sort of segues us into the infamous loop heat pipe anomaly striping. You'll see this as the graphic moves through the time of day. As we approach and then come out of saturation, various infrared channels exhibit this striping behavior. As we all know, this is because of the thermal anomaly with GOES 17, unable to maintain a cold, stable temperature for the detectors. As they warm and cool, they respond at different rates from their neighbors to incoming radiance, and that's what gives you the row to row striping, similar to what we saw last slide. And in terms of mitigation, I mean, what haven't we done? The whole team across the board has done so much to really improve this as best as we can, and is doing a fantastic job. We have our semi-annual yaw flip to keep things as cool as possible, and we actually have one of those coming in a few weeks, I believe. One of the biggest calibration algorithm updates we've done on the ground system since the launch of GOES 16 is predictive calibration. That went into ops last summer. And in a nutshell, that takes your current view of your internal calibrator target, the black body, as well as the previous, and uses those two to extrapolate calibration parameters forward into the future. It also does the same for when we do a view of cold, dark space every 30 seconds. That's used to subtract the dark noise. Integration times, just like with the camera, you can just change your exposure time. We can do the same for ABI and shorten the integration time to hold off saturation as long as possible. That's also called the gain set switch. That happens seasonally, twice a day. And of course, we've done, tweak some parameters and optimize things within the lookup tables. And we introduced the cooling timeline recently to try to limit the heat load on the detectors. So all these have worked pretty well. We've cut back on the amount of saturation. We've improved the striping before and after. One unfortunate thing is two of these mitigation strategies, PCal, predictive calibration, and the gain set switch, they can collide. we call it the collision. So I mentioned PCal looks at the current and the previous calibration look. Well, if in between those two, you change the integration times, now your current calibration counts look nothing like your previous one. And so if you try to use those two to extrapolate into the future, you get junk. And it can manifest itself in a few different ways. That's why I have different examples here. On the low end, channel 12 shows sort of severe striping, but you can still make out some scene content. Channel 13 just goes missing for half of that hemisphere. Channel 15 shows you start off in the northern hemisphere, not bad, but you get sort of a gradually increasing calibration bias. And then there's whatever's happening with channel 16. So that's how it happens. That's why it happens. You get this collision of the two different things. To mitigate it, what we have been doing, and we've done it pretty successfully, this actually doesn't occur very often because other people on the pro team have been very diligent and very good about coordinating with the operators to get the timing and the dates for the gain set switches, and by using some magic with lookup tables, forcing PCal to operate within those times so we don't get these collisions. And that's worked pretty well. A lot of hand-holding, but it's been worth it to avoid this. There is an enhancement to the algorithms in work that would sort of allow this to happen, to deconflict these two, and that's in work hopefully for the near future. There's one more sort of real calibration type anomaly, and that's where you get these darkened bands over an image, and this is GOES 17 only, and I'll explain why in a second. It could end up as missing bands, as you see down here in the full disk. This is when I mentioned we do a look of cold, dark space every 30 seconds. Well, periodically, the bright, warm moon happens to be there. And nominally, the algorithm will notice that, discard that space look, and just reuse the previous one because it's good enough. It's only 30 seconds old. It will use that until you do the next one, and 30 seconds later, you're looking at a different part of space. The moon's not there. Everything is fine. And that's what happens with GOES 16. For GOES 17, we had to disable that functionality just to optimize the imagery the rest of the time. And so periodically you get these darkened stripes. It's darkened because, again, I mentioned that cold, dark look of space. That's sort of like the dark noise that gets subtracted from the Earth counts. And so when space is brighter than it should be, that delta is smaller than it should be. And so that just looks dark. And if that delta goes to 0, you get missing data, as you see down here. So the reason in the full disk example here, it's persistent for half of the full disk. Well, I mentioned we do a look of that internal calibrator every 5 minutes for Go 17. We also do a view of space just before that. So if the moon happens to be in that space look, which is much more rare, but it does happen, then the calibration parameters that you get from the view of the calibrator are junk. And you can see that persists for the first half of the mode 6 timeline. Midway through, we do another look of that black body with the space look. Moon has moved on, things work out, problem solved. Right now, the only mitigation is to deal with it. Unfortunately, there is an enhanced lunar rejection algorithm that would work with Go 17, and that is in work along with what I mentioned in the previous slide. So those were ones that take a little bit of explanation of the calibration processes. These next few are a little more straightforward. Caterpillar tracks. These are narrow, skinny, vertical bands of missing data. Actually, in this first one, if you look closely, you see sort of a checkerboard zigzag edge to it. That is traced back to what I showed initially. Those detector columns have like a checkerboard appearance for the active detectors. That shows up here for missing data. And essentially, this is when we drop a packet or two of L0 science data somewhere between the satellite beaming it down or within the ground processing itself. And the ground vendor, we have a request to them to really do a deep dive and see if they can trace where in the system this is happening. These are sporadic. They usually only last for a swath or even a couple instances within a swath like this, but they're not persistent and long term. But closely related to caterpillar tracks are the shark fins. And you can even see before this shark fin, we had a caterpillar track earlier in that swath. Shark fins are this triangular shape of missing data, although if you look closely, data isn't actually missing, it's just smushed to the side somehow. And it's really warped over there. This is also sporadic. It's just because of data loss somewhere in the system, but instead of science packets containing irradiances, this is probably a telemetry packet loss so that the navigation can't quite work right. And again, much like caterpillar tracks, the ground vendor is doing a deep dive into why this might be happening and where. Cold pixels around fires, which got the really rolls off your tongue acronym of CPAF. This is where, in channel 7 only for both satellites, if you have very bright, hot fire pixels, next to it you can get artificially low or cold pixels. And actually, we've seen the inverse. We have seen hot pixels around ice as well. So this is not in the raw data ABI collects. Rather, it's a numerical artifact of that resampling step that I showed in the algorithm earlier on. That resampler is optimized for the other 99.99% of the pixels for the rest of the imagery, but just because of the math, this can come out. We have mitigated it though. Earlier last year, we deployed a modified kernel, which is in the sense of a lookup table. We deployed those for both satellites April of last year, and that has cut back on the magnitude and the frequency of these, but I'm not sure it'll get rid of it completely. So you may see this from time to time around hot fires. Doesn't mean it's actually cold right next to it. And then solar farm glints. The concept of glint from a geostationary satellite, that's not new, but typically we've seen that from oceans and bodies of water. This is a bit new because the increased resolution on ABI lets you resolve the solar farms. Also, solar farms are a relatively new thing also. So you get this region of saturated pixels as well as these vertical bands of ringing coming out from the top and the bottom. This will persist just for the one swath, maybe in a couple products. Like this is from a CONUS. Perhaps if the meso that happened a few seconds later caught this region, you would get it there as well. But this is because the geometry between the sun, the solar panel, and ABI is just right to get direct reflection into ABI's barrel. The ringing, we suspect, is because of either the photons spill over to their neighbors, or there's just electronic crosstalk, or something on board the instrument just can't handle that flood of photons in such a tight spot, so it spills over like that. So this happens with very fixed geometries. That means it also happens every time we get that tree. You see here, this was early June, a few weeks before the solstice, as the sun was creeping northward. That means a few weeks later, as we're coming back from the solstice, this geometry would have presented itself again, and if it's cloud-free and the conditions are just right, you'll see it then as well. So I think that's the last one. Yeah, that was all that I had. If you're looking for a deeper dive on any of these, more information, I'm a co-author with some people at the University of Wisconsin on an article for the upcoming edition, the GOES-R specific edition of the Journal of Applied Remote Sensing. That is in publication, and we hope that comes out in the next few months. So look for more information there. Or if you see something we didn't cover here, something you can't explain, by all means, reach out to myself, or we have the GOES-R User Services Coordinator. Joe Fiore is part of the pro team as well, so he can reach out to us if you contact him. So that's what I had. Thank you for your attention, and I'll take any questions. Thank you.
Thanks, Dave. I appreciate it. As Jordan said, this is Chad Gravel from Southern Region Headquarters, and I'll be facilitating the discussion today. And we have a couple questions in chat, but I have a few to maybe start things off, since we have about 10 minutes or so. At my old position at the Operations Proving Ground in Kansas City, we were lucky enough to get GO16 imagery basically a month before the field in AWIPS. So it was in that February 2017 time period, and we were looking at the imagery a lot and providing feedback to the pro team. I guess my question is, do we expect to see any new artifacts that maybe you haven't noticed or haven't seen by users yet? I think I know the answer to that, because we've been going through this imagery, with a fine-tooth comb for so long. But I was wondering your thoughts on that.
We'll never say never, I guess, especially as we launch 2 more satellites, in the future. There's always a chance that something new could pop up that no one's noticed yet. But right, by now, we've been through many seasons. Right. We've had lots of unique, geometries with the sun, the moon, all kinds of things. We've had loop heat pipe issues. I would think we've seen it all by now. But again,
okay,
that's
cool.
Famous last words, right?
No, I understand. Let's talk about the loop heat pipe anomaly for a few minutes. Is there anything else that's being done to mitigate it outside of what you discussed, on those slides?
I'm not sure there's anything coming that will have as big of an impact as yaw flips and integration times have had in predictive cal. There's a few parameters that actually, it's something we've been discussing with the science team these past couple of weeks. A few parameters here and there that may help improve some of the midwave channels here and there as you approach the saturation. So that might bias back a little more imagery, or bring some of the non-saturated imagery into a little bit of a better calibration alignment. But I don't think there's anything quite so major coming anymore.
Okay, sounds good. What other algorithm or LUT updates are in work by the science teams that maybe you haven't discussed here?
They're sort of in the weeds. In terms of algorithms, I mentioned the collision fix, the enhanced lunar rejection. There's one that with the bad detectors, I mentioned that dead row list. Currently, that's deployed as a lookup table. Algorithmically, we may be able to utilize that functionality on its own without human intervention. There's still some details that we're sorting out between the two vendors and the science teams before we hit the go button on that. As for lookup tables, we're getting to the point where we're really chasing the small errors. So as a calibration scientist, you would see some improvement in the numbers, but visually it might not be that apparent to a user.
Okay, so one of our questions from the audience was from Brian Mata, and he might need to elaborate on this, but I'll let you decide. And he's just wondering why there are so many dropouts, anomalies of the GO16 ABI imagery that result in missing imagery. You know, if you need him to, you know, explain more, we can get Brian to do that. You know, one of the things that one of my hypotheses is we just have so much more data. You know, I think, you know, when you compare that to the legacy GOES 13, 14, 15, I would assume that probably plays a role. But do you have any thoughts on that, Dave?
Yeah, I would go there as well. Sort of speculating, we think some of the dropped packets that give rise to shark fins and caterpillars and maybe just wider chunks of missing data. If it's within the ground system, you know, those packets, once they hit the antenna, they get routed all different which ways, and there's load balancing between different servers and network optimization. And if any of that suffers even a little bit, of the millions and millions of packets you get each day, you know, one or two of them go missing, that's a pretty good success rate, but it does show up in the imagery. There is a server refresh about to start with the ground vendor. I don't know the details that closely, but you know, the hardware is getting refreshed in the coming couple of years. Perhaps that could help, but that's speculation at this point.
Yeah, and you know, I think, like, and myself included, you know, we take this for granted, right? Like, you know, how much data is being sent back and forth, because in our display software visualization, it just appears. So I really appreciate, you know, this discussion and, you know, how much transparency there is between, you know, your team in trying to fix these problems to make this imagery even better than it already is. We have a few more questions, but I feel like we should pause, you know, and I'll pass it over to Jordan to conclude the session, but by all means, we can answer more of these questions if other people decide to stay on the call.
So thanks, Dave. Thanks, Chad. As Chad said, we're going to wrap it up officially here, but Dave and Chad are going to stay on a little longer. If you have some questions, you want to talk one-on-one, we'll extend this session a little bit after this formal wrap-up. Understand that your time is valuable and some of you need to get on with your day. I'd encourage you to join us next week, Thursday, August 27th, again at 12 noon Eastern time. John Evans and Lee Byerly from our Tower S team will be giving an overview of the upcoming version number 19 of the Tower S RPM and what that will entail. So a couple new things coming forth on the next Tower S RPM. If you're interested in that, please join us again next week. Really appreciate that. And then there is a survey in the chat from David Blutis. You'll see fairly shortly. Any feedback you have on this session or the Satellite Book Club, we're still trying to improve, make this the most valuable use of your time. So I know you get overloaded surveys, but if you have an idea for us, please let us know. So with that, I'll turn it back over to Chad, and everybody that wants to stay on can continue the discussion. And once again, for everybody that has to run, have a good rest of your week. Thank you, Dave. Thank you, Chad.
Great, thanks, Jordan. So Dave, here's another question. Let's go back to basically it's related to loop heat pipe, but talk about how the GO17 detector is cool. You know, maybe in a little more detail on a day-to-day basis, because they are, while you know the sun points at the satellite every day, you know, there's obviously certain times of the year, you know, that are more problematic, at least with GO17. So can you maybe get in a little more details on how what is normally done? Well, what is done to cool those detectors?
Sure. Yeah, there's active coolers in the system, and they basically try to scoop up all the heat and through the loop heat pipes carry that to the radiator panel that sort of sits on top of ABI. Anomaly would go, I think, up north. And those loop heat pipes are what, there's the congestion within them to prevent that efficient flow. So if you look carefully at the animation, you will see the Cookie Monster effect, which means that this is when the sun is going behind Earth. And this is actually a little counterintuitive to myself, even when this first happened. I would have expected the worst degradation to be now when the sun is behind Earth. And you can see it's just below the southern hemisphere. So this is late mid-October. So we're getting into the winter season up north. But instead, what happens is the solar load is peaking at this time, but the cooling system is kind of able to keep up for a little while. It's sort of a trickle-down effect where the system gets overtaxed, and it isn't until a few hours later that heat just can't be dissipated. And that's when the detectors warm. And when they warm too much in the infrared, warm components in the infrared is like having a tiny light bulb in your camera, right? It's emitting photons that you can't control, that you don't want. So that's why we get the striping and the saturation. So, and then as time goes on, by the time you start to come out of saturation, the sun is well to the east, if not behind the satellite. So that direct solar load coming into the optical port is long gone. That cooling system is able to finally catch up, dissipate that heat, and bring everything back down to a reasonably stable and cool temperature for the rest of the day. So that's kind of sort of how it's happening.
Oh yeah, no, that's good. So
Sure.
maybe a follow-up, and please, no pressure if you can't answer this at all. But because I know that some of this information, by many could be deemed sensitive, I suppose. But do we know why, this took place on Go 17 but not Go 16? And I guess, is there any, and I'm sure there is, but we don't hear about these things, especially in the weather service and the field a lot of times. How do we know it wouldn't happen with Ghost T and Goes U, or do we just don't know? And this is just a complete kind of freak anomaly type situation.
Well, at first, why it happens with 17 but not 16, I don't know the details. I know the anomaly recovery team really dug into that to see if there was something in the build that was different, and I don't know those details. Basically, something is causing some congestion within those pipes and just preventing the efficient flow. I do know for the next two satellites, there was a re-engineering of that system that was thoroughly vetted. There was a lot of analysis and discussion. I'm pretty sure that all got greenlit to be in place for T and U. And I believe there's some extra details of that. I think on the GOES-R website, they're discussing the anomaly. Whether it goes into details of the next two satellites, I'm not sure, but if it doesn't already, it probably will eventually. But long story short, they did do some re-engineering of how that system works to try to improve it.
Okay, great. Yeah, thank you.
Yeah, Chad, if I could just jump in. Sorry, I just posted in the chat for anybody who's interested. NASA did launch a mishap investigation, and the report from that board is now publicly available.
Yeah, good. Thanks, Jordan and Michelle. I appreciate it, because we all have. I don't just do satellite anymore, so I miss some of these things a lot of times as well. Let's see. Early on in GOES-R, there was a period where imagery would wander around. Can you describe what's happening, and do we ever expect to see that again?
We hope to not see it at least not to that severity. So that is tied to this step of the algorithm navigation. In the navigation, so as a remote sensing scientist, I have a pretty good handle on the calibration and resampling steps. Navigation is really complicated. It utilizes periodic views of stars to get a real precise understanding of exactly the orbit and attitude of the whole satellite and where ABI is pointing at any given moment. And that is fed into what we call the Kalman filter, which is sort of like a continuously running model of that orbit and attitude correction. And that gets utilized then to properly geolocate the samples on Earth before they get resampled. There were, early on in the ground system, there was just some issues with that Kalman filter stability and some of that processing where if it would fail or have to restart, there was some error that upon restart. That has been improved greatly. Some of those teams did a lot of great work to try to improve that and rework the guts of the system to smooth that over. And if there is a restart or if there's a drop, we sort of can keep a steady state instead of starting from scratch. So we hope that was isolated to early on in Ghost 16 and we don't see it again, but that's the quick answer of how and why it was happening.
And somewhat related, there's a follow-up that there were times when the meso imagery would basically go on a quote-unquote world tour. Do you remember that? And then, if you do, what was causing that to happen?
I only sort of remember it. That also is related to this navigation step.
Okay.
The root cause I forget, but if there's something wrong with, again, either the star looks or the processing of them or something within this step, that's what will happen. Your knowledge of your line of sight for every instant of collecting data, if that starts to go wrong, then things can start to move around on you and swim. So sorry, I don't have the details on it, but it's tied to all that.
Okay. No, that's okay. Does anyone, here's another question, does anyone at NESDIS monitor for RFI on the ingest side? And I don't remember what RFI, that acronym, stands for. Maybe is it request for information, maybe, or?
Radio frequency interference.
Okay.
Yeah, it was radio frequency something. So, so on the ground system, there's a lot of tools that basically just continuously monitor the downlink of the raw data, as well as once we make these first round of L1B and CMI products, those get beamed back to the satellite as the GRB packets, the goes rebroadcast, which then distributes it to everyone with a receiver in the hemisphere. So the uplink and the downlink receipt of those GRB packets, all that's monitored pretty carefully by tools and personnel on the system. So yeah, if they see RFI, they're aware of it. If it gets bad enough and it persists, they can swap to the backup processing site, which, it's always a hot backup running just in case you need to swap to it if something goes wrong with the prime site. So that can happen. They're always looking for it. Usually it's just a short burst of something periodically.
Is that information documented for users anywhere?
That's a very good question. I'm not entirely sure. I could reach out to the right people, and see if there is any kind of user-facing documentation on it. I'd have to pass that along after the fact.
Sure, no, it's okay. I think that's all the questions that I had and that were in the chat. Is there anyone else? Does anyone else have a question for Dave that you have? You could throw it in the chat really quick. Or anyone that's unmuted have a question for Dave. Okay, I guess we're hearing none, Jordan. You know, I thought this was great. You know, a great presentation. It wasn't overly technical, which is important. And you know, it just goes to show that, you know, like I said earlier, we, you know, especially users of this imagery and these satellite products, we really take all this for granted, I think. So I appreciate you coming and sharing, you know, some of these quote unquote stories with us.
Sure. Thank you. I appreciate that. Yeah, there's an awful lot of science engineering every step of the way that has to be optimized just right. So it's a testament to how well it was done. The fact that, you know, we have to look at what goes wrong because it goes right so much of the time. So
yeah, and it's continuous too, right? Like I think a lot of people would think it's the first 6 months, or when you're in that you know, that Val more, you know, intensive time period. But this is ongoing to continuously, you know, monitor everything.
Yeah, it's an impressive setup. So I mean, it's just kudos to basically across the board, the whole team, instrument vendors, ground operations, everybody.
Yeah, thank you, Dave. I appreciate it.
Thank you.
Okay. Thank you, Dave. Thank you, Chad. Thank you, everybody, for being with us today. And thank you to all the engineers that keep GOES-R running. We appreciate it here in the Weather Service. We've got the information for contacting the Tower S team up on the screen. Remember about the survey. Take care. Have a good rest of your summer.